Okay, in this video I'm going to illustrate how to carry out principal components analysis using SPSS. Principal components analysis is generally utilized when you have a larger set of measured variables and you want to reduce that set of variables down to a smaller set of components. Basically, the components are like latent variables that help to summarize or explain the variation in the original set of measured variables. So for this reason, components analysis is oftentimes utilized as a data reduction technique. So for instance, let's say I want to run a regression analysis and I want to predict variation in some dependent measure. And let's say that I have a larger number of measured variables that I'm considering as predictors for inclusion in the regression analysis. What can happen is that when you have a large number of predictor variables, you can run into problems with collinearity and kind of upset the results of your regression analysis. Basically, you can end up with, even though as a set the predictors explain significant variation, perhaps you end up with none of the predictors actually being statistically significant. So, when you run into problems with collinearity in the context of regression, your standard errors are larger, and oftentimes you can end up with non-significant results when it comes to testing the individual regression parameters. So that's one example of, so what I might do is perform components analysis, try to reduce the larger set of measured variables down to a smaller set, and include component scores as predictor variables in my regression. So that's just one example of using principal components analysis as a data reduction technique. Components analysis is also utilized sometimes as a way of just basically like standard common factor analysis, and basically just trying to explain a latent structure associated with that might help to explain the pattern of correlations among a set of measured variables. There's considerable argumentation about utilizing components analysis in this way. One of the arguments is that common factor analysis and components analysis are mathematically not equivalent procedures, and because with components analysis you're explaining the variance as opposed to just the covariation among measured variables, then it's not necessarily appropriate to utilize components analysis to discover the covariation in that way. So at any rate, it's just something to keep in mind. Those are some common ways in which components analysis is utilized. And what I thought I would do is take a set of measured variables, basically items from a scale, and illustrate the procedure. Like I said, it is generally recommended, at least among a fair number of individuals, that if you're utilizing components analysis to discover latent structure that is producing intercorrelations among your measured variables, that you utilize some other common factor analytic technique like principal axis factoring. But in this case, I'm just going to utilize this to basically create a set of component scores that based on data from responses to a set of survey items. So here I have a set of data in SPSS, basically responses to 16 survey items. And the survey items are these right here. So you can see I would prefer complex to simple problems. It upsets me to go into a situation without knowing what I can expect from it. I like to have the responsibility of handling a situation that requires a lot of thinking. I'm not bothered by things that interrupt my daily routine. Basically, these items were sampled from the personal need for structure scale and also the need for cognition scale. It's also notable that so basically the odd items are actually the need for cognition items, and the even items are actually the need for structure items. Also, you'll note that basically some of the items in the scale are actually reverse codes that are reverse coded items that are part of the original scale. So, for instance, thinking is not my idea of fun is an example of a reverse coded item associated with the need for cognition scale. And the basic idea with those kinds of items is that that a person who responds low to that item is actually responding higher on the need for cognition scale. So generally speaking, with items such as this, you end up reverse coding those items in order to make higher values consistent with the affirmation of higher need for cognition. You also have, as an example, which is another example of a reverse coded item would be, I try to anticipate and avoid situations where there's likely a chance I have to think in depth about something. So that's, again, that's a negatively worded item that would need to be reverse coded if I was, constructing the need for cognition scale from data from these sets of measured variables. As an example, I find that a well-ordered life with regular hours makes my life tedious. That's actually a reversal that is reflects the opposite sentiment of somebody theorized to have be higher in need for structure. So at any rate, so you can see that the items reflect different content and also some method aspects as well, which is you have some items that were written in the affirmative to tap the constructs of need for structure and need for cognition. Other items that were written to reflect the contrary sentiment, and so before scoring those items and including them in a scale, you would actually do a reverse coding of those items. So what I thought I would do is, and by the way, one of the reasons why items are set up in this way, like using negatively worded items, is because, quite frankly, it's to help deal with response bias in a scale. A lot of times when people respond to measures of different constructs, what will happen is that folks can kind of get in the habit, if they are using something like a Likert type format, where maybe you have 1 equals strongly disagree, 7 equals strongly agree. What can happen is that if everything's worded in the affirmative, it can cause people to basically either endorse all the items or indicate low agreement with the items. And so basically the reversals are there to help to kind of prevent people from kind of moving into a sort of an acquiescent response set. So at any rate, we have we have data on 16 measured variables, these items in the scale, and basically we have, in our data set, we have 198 cases, and there are a few little pieces of missing data in there, but we have 198 cases. So, and what I thought I would do, just for starters, is I would go ahead and create, just go ahead and reverse code those items. We already know what the items are designed to tap, which is need for cognition and need for structure. And so what I thought I would do first is to just go ahead and perform the reversals so that in general responses to these negatively worded items, a low response would be recoded as high on that particular construct. So I thought I would start off there. So in terms of the, so what I'll do is I'm going to use the transform function and recode into different variables. And so so in terms of the items that need recoding, given my objectives, they will include items 4, I'm not bothered by things that interrupt my daily routine. 5, thinking is not my idea of fun. So I'm going to just really quickly use item 4, item 5. The other items, let's see, I have 7, I would rather do something that requires little thought. That is a need for cognition item that's reverse coded. So I'm going to move 7 over here. Then I try to anticipate and avoid situations where I have to think in depth. That's also a reverse coded item. So that was number 9. I believe number 10, I enjoy being spontaneous. That was actually a reversal for the need for cognition scale. Need for structure scale. Let's see, I find well-ordered life with regular hours makes my life tedious. That will be a negatively worded item. That's number 12. We also had number 13 was a reversal for the need for cognition items. Then we have, that was the only think as hard as I have to. 14, I don't like situations that are uncertain. That's affirmative for the need for structure measure. And then thinking about small daily projects, that's number 15. That's actually needs reverse coding. So I'm just going to go ahead and reverse code these just to make these consistent in terms of directionality with the way that the scales are scored. So I'm just going to create a new set of variables. So I'm just going to call it IT R4 change RT. Let's see, IT R5, IT dot R7, RT or IT dot R9, IT R10, IT R12, IT RT13, and 15. Okay, so what I'm basically going to do is recode the data from those original set of measured variables into a set of reverse coded items to again reflect higher scores on these particular items, reflecting an affirmation of the constructs that we were looking at. So for the old and new values, basically I used a 7-point Likert type format. So basically 1 was strongly disagrees, 7 was strongly agrees. So I'm going to recode these particular items. From 1, I'm going to recode it into a 7. So a person who was strongly disagreeing now becomes a person strongly agreeing, which is in the affirmative for that particular concept. So we have 1 to 7, 2 to 6, 3 to 5. Obviously, we have a midpoint of 4. I'm just going to leave it alone. But I'm going to use that just as a placeholder. And 5 to 3, 6 to 2, and 7 to 1. Okay, so you can see right here it just says 1, 2, 3, 4, 5, 6, 7, 7, 6, 5, 4, 3, 2, 1. That's how I know that that I've done the recoding properly. So then when I click on OK, you can see that now we have our new data set that has now the reverse coded items in this. So I'm just going to include these reverse coded items when it comes to actually performing the components analysis. So that leads us then into actually performing the components analysis. So we'll start by, to run it in SPSS, we click on Analyze, Dimension Reduction, and Factor. So, in a nutshell, what I do is I'm going to move all the variables that I'm factoring or running the components analysis on over to the variables box. So I've got 1, 2, 3, and one of the annoying things seems to be that SPSS creates these. It's defaulting by giving me nominally scaled variables. Not that it mathematically is going to matter when I actually perform the analysis, but I want to just clean that up and make sure that everything is in the scale for the measure. So let's go back. We'll go dimension reduction factor. So I'm going to say 1, 2, 3. I'm going to move item 4 over, and item 5, the reverse coded items. I'm going to add in item 6. We know that 7 is reverse coded. And move 8 over. We had 9 and 10 that were reverse coded. Number 11. Then we're going to use 12 reverse coded and 13 reverse coded. Then 14. 15 was reverse coded, and then 16. So the first question that I need to ask or address is whether or not my correlation matrix is factorable, and whether it's appropriate to actually carry out the analysis. So I can go into descriptives, and down here you've got KMO and Bartlett's test of sphericity. So a lot of times people will generate this when they run the analysis and interpret everything together, but I'm going to just do this separately, because really the question is, first of all, is the matrix actually factorable? So if I click on this and click on continue, I'm just going to leave all the other defaults as they are for right now, because I want to walk you through that in a second. So when I click on OK, you can see that I have the defaults are on, and basically this is just generating the components analysis using an eigenvalue cutoff rule of 1, and we'll talk about that shortly. But the KMO and Bartlett's test, basically when I'm looking for the KMO index right here ranges between 0 and 1, and values that are closer to 1 indicate that your matrix is more factorable, and that it's really more appropriate to carry out the factor analysis. There are some various rules of thumb for what constitutes a good factorable matrix, and one that you would want to actually carry out the analysis on. So because the thing is that basically components analysis and other exploratory factor analytic techniques really involve largely doing the analysis on a correlation matrix. So we need to know if the matrix is actually factorable, and whether or not it's actually appropriate to carry out that analysis on a given correlation matrix. So in our data set, we have correlations among all these measured variables, and so we want to see if it's actually appropriate to carry out the analysis given our data. So in terms of the KMO index right here, then basically, like I said, closer to 1 the better. Basically above 0.7 would be considered adequate to good factorability of the matrix, and so you can see that we're at a 0.792. Values that are in the 0.6s, 0.5s, and on down, you're talking about it becomes less and less appropriate to run the components analysis on that matrix. But at any rate, that's just sort of a rough way of thinking about the KMO measure. For Bartlett's test of sphericity, this is a significance test. This is testing the degree to which your correlation matrix differs from an identity matrix. And with an identity matrix, what that means is that in the primary diagonal, the elements are all 1s, and on the off diagonal, the elements are all 0s. So it's kind of like a null correlation matrix in a sense. Basically, there's no relationship among the measured variables, and you're trying to test whether or not your correlation matrix from your data differs significantly from an identity matrix where you have no correlations among the measured variables. So if this is statistically significant, and this is your p-value right here, then that would indicate that it is more appropriate to carry out factor analysis or components analysis on the correlation matrix. So in this case right here, our data actually does seem to, it does appear to be statistically significant, and then carrying out the components analysis makes sense. So given that, like I said, I've already run the components analysis in the context of requesting this, but so you'll notice that So if I reran it again with those same defaults, these are it. So the thing is that, like I said, with components analysis, the idea is that you want to generate a set of components that explain the bulk of the measured bulk of variance in the original set of measured variables. So the idea is that we're trying to summarize as much variation in the original set of measured variables as possible. But also kind of adopting the principle of parsimony. So we're trying to explain the most of the variation in the original set of measured variables with the fewest number of components possible. And so essentially what happens over here in this little box where it says total variance explained, you'll see you've got components, and then basically what happens is that the number of components that are extracted during the factoring process basically will equal the number of measured variables that you originally had. And so when you look in this column right here, this column, and this column, you'll see again you've got 16 measured variables, 16 components, and that corresponds to the fact that we had 16 measured variables that we were running the components analysis on. This column right here gives you eigenvalues, and an eigenvalue is just basically is a variance index, and basically it summarizes the number of measured variables that the variation in the original set of measured variables is accounted for by the component. So you could think about it this way, that the first component accounts for as much variation in the measured variables as 3.969 of the original set of measured variables. So it's kind of rounding it off to 4, we could say that the first component accounts for about as much variation as 4 of the original measured variables. The second component accounts for about almost 3 of the measured variables. So it's accounting for as much variation. Now keep in mind that it's not saying that you're accounting for exactly 3.9 like item 1, 2, and 3, and it's accounting for just those 3. It's the variation accounted for is distributed among all of the measured variables themselves. So we're accounting for as much variation as almost 4 measured variables. We're accounting for as much variation as the variance found in 2.8 variables. For the third component, we're accounting for as much variation as can be found in 1.29 of the original set of measured variables. The fourth one, so forth. And so in the percentage column, you get the percentage of the total variation in the measured variables accounted for by the components. So you can see the first component accounts for 24.8%. The second component accounts for 17.58%. The third component accounts for 8%, and so forth. So you can see that the eigenvalues associated with each component are decreasing. And so when you get down to less than 1, you're basically saying that the component explains for less variation than a single measured variable. And so all of these eigenvalues right here are reflecting that. If you had an eigenvalue that is 1, you're basically saying that the component explains as much variation as a single measured variable. So you can see that the percentages are decreasing in terms of the proportion of variation accounted for, or percentage of variation accounted for in this original set of measured variables. In the cumulative percent column, this is reflecting the, you guessed it, the cumulative percentage accounted for by each component and those preceding it. So for component 1, the cumulative percentage will equal the percentage of variance accounted for. For the second component, you're accounting for 42%. That basically this 42% is accounting for the variance accounted for by component 1 and component 2. So if we take these percentages and add them together, we can say that components 1 and 2 combine to account for 42.39% of the variation. The third component, if we add that in, then we can say that it accounts for another 8%, and components 1 through 3 account for a little bit over 50% of the variation. So you can see that the cumulative percentage for the last at component 16 will account for 100% of the variance, because that takes into account the percentages accounted for by each component that precedes it. So So when it comes to running the analysis, there are various strategies. Basically, one of the things that we try to do is to identify those components that explain most of the variation. So we're basically trying to identify a subset of the components that really do the best job of summarizing the overall amount of variation accounted for in the original set of measured variables. And so there are various decision rules for deciding on how many components to retain. One decision rule is called the Kaiser criterion, and basically with that you essentially identify those components with an eigenvalue that's greater than 1 and retain those components. And so the basic idea, if we go back and rethink what the eigenvalue is, we're basically saying that a component has to account for at least as much variation in the measured variables as one measured variable. So if you have an eigenvalue that is less than that, if you account for less variation in the original set of measured variables than one measured variable, then in that particular case, those at that point everything following is dropped off. So right here, the default in SPSS, if we go into dimension reduction, you can see under extraction that the default method is principal components, and you see that the retention is based on the eigenvalue cutoff rule. So it says eigenvalues greater than 1 we retain to help summarize the variation in the measured variables accounted for by the components. So the default then was just this. Also, we can utilize a second strategy, which is the scree plot, which gives us a visual depiction of our data and helps us to identify where, how many, which components do the best job of summarizing the variation in the measured variables. So we're going to click on those two right here, and then also click on OK. Commonly, following the extraction process and deciding on how many to retain, we would rotate the data in order to facilitate interpretation. And a common rotation strategy is Baremax. So I'm going to go ahead and click on that for right now, and then click on continue, and then OK. So what you'll see when we've run the analysis, you'll see that we're just going to move down to this box right here, and essentially you can see that basically right here, this is really the same information we saw in the table above, and you'll notice that these are those components that met the eigenvalue cutoff rule. So you can see right here that when it comes to the eigenvalues, all of these are greater than 1, and all these eigenvalues are actually the same as the eigenvalues you see over here. So the cutoff was actually 1, so everything else below is basically treated as basically not important. So you can see that when you met the eigenvalue cutoff rule using 1, 4 components are retained, and you can see that all of these values in these 4 columns are these columns are exactly replicated over here. And so there you go. So you can see that so basically what we're saying, if we utilize that strategy, then we would say, well, that 4 components best summarize the variation in the original set of measured variables, and that is the response variation to the items in our measure. So if we decided at that point that this is suitable, then as a solution, then what we would do is we would go back and interpret the rotated component matrix values, and this is just basically captures structure coefficients, which is the correlation between each of the measured variables and the components themselves. And so what you would do with that is you use the pattern of correlations to name those components. So at this point, we can do that. So I'm going to move down a little bit more because I'm not quite ready to start interpreting the component scores, the component matrix just yet. So another strategy for deciding on the number of components to retain is to look at the scree plot. So a scree plot is just basically plotting out, you have essentially the eigenvalues that are found up here in the above table. So these are the eigenvalues, and these are plotted against the component number. So you can see that component 1 is going to explain the largest amount of variation in the measured variables. Component 2 explains the next largest amount, and so forth. And so what we're trying to do, again, is to come up with a parsimonious solution and summarize the variation in the measured variables with the fewest number of components possible. So the scree plot basically follows the logic that if you think about the side of a mountain, you have the main slope of the mountain, and then you have the rubble at the base of the mountain. And so what you do is you try to visually ascertain where the rubble begins and where the mountain, the primary slope is in the mountain, and so then you make your cut. So kind of visually looking at this data set right here, it looks like that component 1 and 2, it has these two have the highest eigenvalues, and then what happens is that the eigenvalues continue to drop regardless. But you can see that the rubble at the base of the mountain, or the scree at the base of the mountain, seems to start at about component 3. So that actually suggests or lends itself to an interpretation that maybe a 2-component solution makes more sense to interpret than a 4-component solution. In SPSS, it defaults with using that eigenvalue cutoff rule, and so that's not the only rule, and oftentimes using the defaults in SPSS can be problematic. So if I go back and I say I'm going to stick with a 2-component solution, then what I would do is I would go back, analyze dimension reduction, and go to factor, and then I could actually, under extraction, I could force a 2-component solution in order to interpret and just interpret those 2 components. Another option in terms of deciding on the number of components is parallel analysis. And what parallel analysis basically involves is generating random eigenvalues and plotting them against the eigenvalues from your data. So I'm not going to get too technical on the generation of those eigenvalues. It basically just means that you generate a number of random correlation matrices, and essentially so let's say we generated 100 random correlation matrices. We would generate eigenvalues for all 16 components from those matrices, and then we could either take the average or the mean of the eigenvalues associated with each component, or we could take something like a percentile, like the 95th percentile, within the distribution of eigenvalues. And then what we essentially do is we compare them against our raw data. And so in parallel analysis, oftentimes if we were to plot out the eigenvalues, it might look something like this. And so basically this is just a plot of the random eigenvalues, and at the point at which your raw data, the eigenvalues from your raw data become lower than sort of the random process that would have produced the eigenvalues during the simulation, at that point you would make the cut. So everything else, all the eigenvalues down here would be less than those that would be generated through a random process. These 2 eigenvalues would be is from our data. So in that case, we would retain these eigenvalues and cut off everything else. So we can actually go through and in SPSS there's no parallel analysis option, but there are some sort of workarounds that we can utilize. So basically, if you go to this particular website is a good one, and you might be able, you can find other websites as well online. There's also I think Brian O'Connor has some syntax that you can perform the parallel analysis in SPSS. But at any rate, this is a pretty good little engine right here that you can go to generate the random eigenvalues. So essentially what you do is, if you go here, it says number of variables in your data set to be factor analyzed. We had 16 measured variables that we were going to analyze. The sample size for our data set, kind of going back, we had essentially around, what was it? It was around 198. So what I'll do is, if I go back to the little engine here, I'll put in 198, and then where it says type of analysis, the default is principal components. So I'm going to click on submit, and what this will do is it will generate the random eigenvalues. So you can see that you've got means and percentiles. So essentially what happens is that when you generate, if we kind of go back and look, it says number of random matrices to generate, the default is 100. So 100 correlation matrices are generated, and from each of those matrices, and 100 of those matrices, basically you'll have 16 measured variables that are used to randomly generate those matrices. And so you would have eigenvalues for those 16 components for all 100 matrices. So if you take the mean eigenvalue for each component, or if you take the 95th percentile from them, then essentially what you end up with are this column right here of means and percentiles. And so what we do is we compare this against the eigenvalues from our that were generated from our data. So you can see right here that we have an eigenvalue of 3.969, which is larger than the 95th percentile eigenvalue, which was randomly generated. So that would mean that we would retain the first component. The second component has an eigenvalue of 2.813, which is greater than the randomly generated eigenvalue. So that would suggest we retain component 2 in our solution. The third eigenvalue is 1.291, which is less than the eigenvalue generated at random. So at this particular point, we would make the cut. So visually what that means is that, again, if I was to plot out these eigenvalues, the 1.618 would be, falling right around, on component 1 would be falling right around here. The 1.43 would be falling, a little bit more like right around here. The 1.38 would be falling right around, make it a little bit clearer, right around here, and then so forth. And so essentially, if we draw that a line through those points, essentially what would happen is you can see that this would, our data down here is produced, the eigenvalues are less than what would be expected at random, and the eigenvalues for the first two components are greater than what you would expect from a random process. So in a sense, this is kind of like hypothesis testing, to be perfectly honest. So at any rate, using the eigenvalue, using the parallel analysis, it would appear also that a two-component solution is best supported. So if I go to Analyze, Dimension Reduction, now in this case, so I'm not going to stick with the eigenvalue cutoff rule. I'm going to click on Fixed Number of Factors, which is going to generate components. I'm going to type 2, and then click on Continue, and then OK. So now, so I basically forced a two-component solution, which you see right here, and so now I want to interpret those components. So you'll notice that we have a component matrix, which is basically, basically it's like this. If I go back, in fact, I will plot this out under rotation. I'm going to click off of this for the time being and click on Loading Plot. And you can kind of see that basically in two-dimensional space, because we have only two components that are being retained. If we had 3 or 4 or 5 or whatever, then this would be cast into higher dimensional space, and it would be really hard conceptually to wrap your head around it. But you can see that you have for component 1, the component loadings are basically correlations. So, you start at a correlation of 0 on component 1. They go to -1 and +1 on component 2. You've got 0 that would go from negative, and then the range is -1 to +1. So you can see that, for instance, item 1 right here, when you look at the distance between the origin and item 1, that distance is greater on component 1 than the distance that you observe between the correlation of 0 and what was obtained in the matrix for that variable. So you can kind of go up here and look at the component matrix. It's 0.656 and 0.136. So basically, the length of this line is representing the correlation of 0.6. What was it again? It was 0.656, and the second one of 0.136 is being represented in this length. So essentially, item 1 ought to be loading more heavily onto component 1. You can see over here, item number 4, R, you have a -0.29 and a 0.624. So in this particular case, you've got the negative here, which the distance between in terms of the length of this line right here is less than the length of the line that we could draw from with respect to component 2. So 4 is going to load onto component 2. So essentially, looking at the loading matrix, if we didn't perform any type of rotation, what will happen, or it's not going to explode or anything like that. But what can happen is that you can end up with a lot of cross loadings, which makes it difficult to name the component because basically you have certain items or measured variables that would load on both of them. And so what varimax rotation, the aim is to kind of clean up the interpretation. And the way that occurs is, if you think about it, a lot of times you can have a situation where, the items might be kind of falling in this space right here, which is kind of the length of for those items on both of those dimensions is about the same, and so then it becomes really difficult to determine, well, which component those items would actually load onto. And so with rotation, the basic idea is that we leave the relative positions of the items alone, or the measured variables alone, and we rotate the coordinate axes so that essentially the axes kind of go through the data points, and it becomes easier to interpret. So if I'm using varimax rotation, essentially it maintains the orthogonality. This doesn't look orthogonal, but if you just pretend like these are perpendicular lines to each other, and all we've done is we've rotated the component 1 and 2 axes. So in that particular case, to do this, I would just go to dimension reduction factor. Again, I'm just forcing the 2 component solution under rotation. I will click on varimax, continue, and then OK. And basically, after rotation, what happens is that the variance accounted for gets redistributed among the components. So you can see that the eigenvalues change a little bit, but the cumulative percentage of variance accounted for is exactly the same, so which is 42.39, the same prior to rotation and following. It's just that the distribution of the variance accounted for is a little bit different. So if we go down here to our components, go down and we look at the rotated component matrix, these are structure coefficients. So one common rule of thumb is if a measured variable loads at greater than 0.30 or 0.30 or greater, then you would interpret, we would use that particular measured variable to interpret or name the component. So item 1 is really highly correlated with the component 1, and it doesn't meet that threshold obviously on component 2. So the first item in the scale actually was, I would prefer complex and simple problems, which is actually one of the positively worded need for cognition items. Item 2 is loading high on component 2 and very low on component 1. And so the second item was, it upsets me to go into a situation without knowing what to expect, which is consistent with the theme of personal need for structure. The third item is loading highest on component 1 and very low on component 2. And so in this particular case, I like to have the responsibility of having a situation that requires a lot of thinking. That's clearly a need for cognition item. The reverse coded 4 is loading highest on component 2. So remember that basically I am not bothered by things that interrupt my daily routine. We reverse coded that to be consistent with personal need for structure. And so there you go. So you can see that the items, actually, the way that they loaded, really do a nice job of capturing themes of need for cognition and need for structure. So what I'll do is I'm going to name component 1 need for cognition, the second one personal need for structure. Like I said, I'm using survey items here, but I could use items from measured variables from summative scales or whatever to carry out the components analysis. So this is not just utilized in the context of items from, say, a survey. You'll notice that item 12 doesn't really load on either of these, so that would not be utilized in the consideration of when you're naming those components. Another thing to note too is that what you want is there to be a considerable difference in loadings across those components. And so let's say, for instance, I had another item where it loaded at 0.4 on component 1 and 0.3 on component 2. Then it really kind of makes it a little, or let's say 0.35, just to be a little bit more dramatic. So in that case, it would be difficult to determine which component that variable should load onto, because essentially both of them meet this criteria here. And so what you would be looking for is one common rule of thumb for judging which component a measured variable should load onto is basically a difference in component loadings of 0.10 are greater in absolute value. So if the difference is less than that, then you would probably not consider that measured variable when defining component 1 or 2. So in the current illustration right here, if I had, let's say, item 17, and this was the pattern of loading, I may not be inclined to interpret that item 17 relative to the components. So this provided basically a quick overview of components analysis using SPSS. I tried to illustrate several decision rules or decision criteria and for deciding on or decision strategies for deciding on how many components to retain. Also a little bit on naming the components. There are other types of rotational strategies as well, but I just kind of stuck with Varimax because it's one of the more common. So that concludes this video. I hope that you find this helpful.